recording. Okay, so today we're talking about chapter 7, 7.3, and 7.4. So in this version of the book is classes as incremental ADTs. I don't remember anymore the name of the new thing, if it's the same or not. But we're gonna talk about inheritance now. And there's a bunch of interesting things to talk about. So Object OOP allows to define a class incrementally by extending existing classes. It is not enough to say which classes are extended. Our model includes three sets of concepts: inheritance itself, method access control, which we're gonna see, and encapsulation control. So first to talk about talking about inheritance. So this is the very classic understanding of like nothing new per se. A method in class C overrides any method with the same label in all of C superclasses.
Yep.
It may inherit, but in this case they have multi-inheritance, not only single inheritance or simple inheritance. Um, Class B is a superclass of class A if B appears in the from declaration of A. B is a superclass of a class appearing in the from declaration of A. So this is essentially saying that the
It's
leveling of the
recursive.
hierarchy doesn't
Yeah.
matter. Fair enough, they cannot be recursive, right? That kind of
Well,
makes
they
sense.
cannot be mutually. Yeah, they can't be cyclic.
Cyclic, yes, because we are understanding this as a graph. Um, and the cyclicalness cannot also happen in the with like indirection, like multiple levels. So this also doesn't work. Um, and yeah, so this is just an example of being mutually recursive. This is an example of conflicting method names. Well, not names, atoms, because in this case, name I cannot use like intuition. It's just an atom. Cool. Running time is all there is. So this is just saying that this is a very dynamic language, which yeah, very
Classes
dynamic
are.
everything.
Yeah, classic. Classes are objects. Small talk style.
Um, if a program containing the declaration of C is compiled in Mozart, then the system will not complain. It is only when the program executes the declaration that the system will raise an exception. If the program does not execute the declaration, then no exception is raised. For example, a program that contains the following source code, which is gonna break because they have methods with the same atoms, can be successfully compiled and executed. Its execution has the effect of defining the function's strange class because yeah, it is only during the call that an exception will be raised, and that happens because class declarations are only done at runtime. They're not checked at compile time because they are procedures.
Yep.
Cool. This late error detection is not just a property of class declarations. It is a general property of the system that is a consequence of the dynamic nature of the language. There is no distinction between compile time and runtime. I would say that this marketing is a little bit misleading in a sense because I would call your thing like Salem would be properly described as this. Their case, as far as I can tell, is not really clear to me that parsing is done at runtime.
Uh, yeah, Common Lisp is also a good example, right? Because like you start the system, and then the semantics of loading a file is actually exactly the same as the semantics of just piping the file contents to the
Yeah,
REPL.
exactly. So to me, this is a little bit like too extreme of a description for what they are doing. As far as I understand that they do have syntax checking and parsing and lexing in a separate phase than runtime. It's not clear to me that this is all being done in a single phase. Maybe it is, and they just didn't explain it. But for as far as I understood, the
Well, Oz Mozart specifically does have an interactive system, so I guess that counts. But yeah,
well, but having an interactive system it may be implemented in a more dynamic way than the compile version of the thing. Like you can have two different ways of doing the same thing, and like what we did with Karuta, right? When we had the REPL, I had to hook some things differently just because the REPL has the interactive aspect. So maybe they implemented that differently, and in the real compiler, they actually treat parsing and syntax checking as a separate phase than everything else.
I think that's possible, but I don't think that's very likely because Oz descends from Prolog, which descends from Lisp, and I know Prolog, at least standard Prolog, is very interactive as well, right? Although there's a small caveat that in a lot of Prolog implementations, you can't just define predicates in the interactive prompt,
Which is kind of silly.
but which is, yes, kind of silly. But um, I mean, since Oz doesn't actually have predicates, at least not at this level of abstraction, we'll get to that later. Then yeah, I don't see why they wouldn't allow the everything to run at runtime.
Okay, so there's that. A class declaration is an executable statement. Compiling and executing it creates a class, which is a value in the language. The class value can be passed to new to create an object. Yeah, and then he talks about the C++ and Java and many other languages. They have clear separation of those things. In particular, having separation allows you to do more powerful optimizations and more dedicated checks for each phase. And you don't. And the great benefit is that those optimizations come without having to run the program. This is the same. This is the same thing as we've seen before. And yeah, and then this conclusion, which is also obvious, if you're not checking anything and you're just letting it fail at runtime, your compiler not only gets simpler, but it also gets smaller. Since the compiler does not actually execute any declarations, it needs very little knowledge of the language semantics. The compiler does in fact have some knowledge of language semantics, but this is an optimization that allows early detection of some errors and more efficient compile code. More knowledge could be added to the compiler, for example to detect class hierarchy errors when we can deduce what the method labels are. Cool. And then it comes static versus dynamic binding. I didn't know that these behavior had these names.
Oh,
Um,
this is one example of dynamic binding. It's not the most general way to do it, but it's one way to do it.
um, yeah, and this is talking about the like which method do we call when you are in a class hierarchy. When executing certain object, we often want to call another method in the same object to do a kind of recursive invocation. This seems simple enough, but it becomes slightly more complicated when inheritance is involved. A common use of inheritance is to define a new EDT that extends an existing EDT. To implement this correctly, it turns out that we need two ways to do a recursive call, which is the topic of static and dynamic binding. So now we have an example of the account class that we defined before, 7.6, which is this. And the thing that matters is this transfer method. Um, so we can transfer money to it with transfer, inspects the balance with that, and do a series of transfers with that. Note that the batch calls transfer for each transfer. And now we want to extend this class with another one that does logging. One way is to use inheritance by overriding the transfer method. So yeah, we're going to make another transfer, which is well, that's that. Then there's the question: how do we know which transfer this is? Where log obj is an object that keeps the log. Let's create a logged account with an initial balance of 100. Now the question is, what happens when we call batch transfer from the original one? There's also this question and the question about okay, but what about the superclass method that was also using the transfer? Is it called the old one or the new one? We can deduce what the answer must be if we assume that a class is an ADT. Every ADT has a set of methods that define what it does. For a logged account, this set consists of the getBall and batch transfer methods defined in the superclass, as well as the new transfer method defined in the subclass itself. Therefore, the answer is that batch transfer must call the new transfer in logged account. And this is called dynamic binding. It is written as to a call to self, right? Um, okay, I have a question. Why are we calling this dynamic?
Because actually, this mentions this in the next paragraph. But the point is, um, if this is not actually like if you make a class that inherits from this one, and that class overrides the method you're calling, you're actually going to call the new version of the method, not the one that's defined locally.
That doesn't answer my question really,
Because you
but
can't know by just looking at this class statically in
yeah,
isolation.
I think that is the real answer because all of this is being done at runtime, right?
Yeah.
So if we were to do these checkings at compile time, then it would not really be called static because in this book's definition, static has a specific thingy like defining the class and whatever. But it would be static binding, even though you're calling self and stuff, right?
Yes, the concrete method you're calling is resolved at compile time, that implies that, yeah, this wouldn't be runtime extensible, right? So it would
Yeah.
be, in fact, static binding, even though it would look like it's dynamic if the syntax
Yeah,
is
I
the
think
same.
that's the best definition of dynamic so far. It is extendable at runtime. Extendable at runtime. I think that says it all. Yeah, and here's the explanation. So when account was defined, there was no logged account. So this must be done in this particular case of OS at runtime. And we're going to be dynamically changing something when the program is already running. Using dynamic binding keeps open the possibility that account can be extended with inheritance, while ensuring that the new class is an ADT that correctly extends the old ADT. That is, it keeps all the functionality of the old while adding some new.
Actually, I want to make a small aside. This notion of dynamic binding is slightly different from what people doing language design think about when they say dynamic binding. We can talk about that later, but it has to do with. Remember when we were talking about how to do the logger, and I mentioned, oh, actually, yes, we could do dynamic binding to solve that problem, and
You
that
said
would
dynamic
avoid
scoping
mistakes.
though.
Oh, dynamic scoping, yes. When we say dynamic binding, usually we refer to dynamic scope, but actually, um,
That's not the same semantics as this.
yeah, it's not the same semantics as this, exactly. So, same terminology. Man, dynamic is such an overloaded word in programming.
But
It's
in this particular case,
crazy.
I don't think that that is the case because that what you talked was dynamic scoping. Scoping.
Yeah,
The notion of dynamic in both definitions is kind of similar. You are doing something, you're defining or redefining something when the program is already running. That is
yeah.
both true for binding and scoping.
It is actually, yes.
So I think in this particular case it's completely fine. Like this is not warming the brain. This is correct. I just think that if the community assumes that binding is equal to scoping, then we have a problem. Um, However, dynamic binding is usually not enough to implement the extended ADT. To see why, let's investigate. Yeah, and then the question happens: what if you do want to call the old one? And then it actually pops up a second question: which old one? Because you may have a hierarchy of classes. And then the answer is that you're going to specify which class it is. So that's okay.
Yeah, this is actually more powerful than what you can typically do in most mainstream OOP languages. Because, like, for instance, in Java, you can call the method of the current class, and you can call the method of the superclass, but you can't specify, oh, I want to call a method from a class 3 generations back, you know?
Exactly, but as far as I remember, when we did Racket OOP, I also don't remember having a way to do that. I
Because
remember
Racket's,
calling the super one, though.
yeah, because Racket's object system is in part inspired by Java, so,
Yeah, yeah, but this is very convenient that you can actually specify which generation you want, and I think that's can completely make sense, right?
it does.
Um, we're not going to use dynamic binding for that. We're going to use static binding, and this is the syntax and so on. And then here's a summary of the true dynamic binding uses the self. This is just a syntactical hint in OS because, as we mentioned, if that was all checked at compile time, even though you're using self, that would be an example of static binding. But in OS, if you see self, this is dynamic binding. And if you see the class name comma, this is a hint of a static binding. This chooses the method matching M that is visible in the class C. This takes overriding into account from the root class up to the C, but no further. If the object is of a subclass of C that has overridden M again, this is not taken into account. Yeah, because you're specifically asking the version of that particular class, so overriding doesn't mess up with that. And then controlling encapsulation, and this is actually something new to me. I never heard of the private meaning that is not the C++ or Java one. Um, okay, but let's read what this is first. The principle of control encapsulation is to limit access to class members, namely attributes and methods, according to the requirements of the application architecture. Each member is defined with a scope. The scope is that part of the program text in which the member is visible. Usually, the scope is statically defined by the structure of the program. It can also be dynamically defined, namely during execution. And then we have typical keywords to express that, such as public, private, and protected. But we're also going to see that these terms
They
are
mean
also
different.
overloaded
Yeah, they
because
mean
they
different things
mean
in
different
different
things.
languages.
Yeah. So the two most basic concepts are private and public. A private member is one which is only visible in the object instance. The object instance can see all members defined in its class and its superclasses. Thus, private defines a kind of vertical visibility, and this is the small talk and noise understanding of private. So that means that if you have something private in C, I3 will be able to observe that, but not
Yep.
I2 or I1. And a public member is visible to everybody. Um, these definitions of private and public are natural if classes are used to construct ADTs. First of all, a class is not the same thing as an ADT it defines. The class is an increment. It defines an ADT as an incremental modification of its superclasses. The class is only needed during the ADT's construction. The ADT is not an increment. It stands on its own with all its own attributes and methods. Many of these may come from the superclasses and not from the class. Second, attributes are internal to ADT and should be invisible from the outside. This is exactly the definition of private. Finally, methods make up the external interface of the ADT, so they should be visible to all entities that reference the ADT. This is exactly the definition of public. Okay. So constructing other scopes. So now we're gonna try to figure it out how to implement the normie way of doing this.
Turns out lexical scoping is ridiculously powerful.
Well, we're also using the fact that we have logic variables in this case.
Not logic variables. Actually, they are using name values, which are unforgeable, right?
Yeah, but how are the name values implemented?
Well, there's a primitive that gives you a fresh name value that's unique, and nobody else has access to it other than you. We saw this way back when we were still looking at
Yeah,
wrap and unwrap, remember?
I remember that, but A is a logic variable in this case. We are abusing the lexoscoping here, as you're right, but the A being unbound is actually what does the whole trick.
Well, yes, that's a syntactic trick. You could write it explicitly, but that's kind of inconvenient.
Yeah, so for example, it is possible to express private and protected scopes in the C++ and Java sense using what is making the method heads instead of atoms when making them name values. A name is an unforgeable constant. The only way to know a name is if someone gives you a reference to it. In this way, a program can pass the reference in a controlled way to exactly those areas of the program in which it should be visible. And why is this more secure? Because the atom, you can guess the name of the atom. With the named value, you can't do that.
Yep.
In the examples of the previous sections, use atoms as the method labels. These are not secure. The third parties can try to use the print representation of the atom and call the method himself. Names are a simple way to plug this kind of security leak. I would say to patch, not to plug, but okay. This is important for a software development project with well-defined interfaces between different components. So let's see how we can do that. When a method head is a named value, then its scope is limited to all instances of the class, but not to subclasses or their instances. So this is a horizontal thing, as you can see in this figure here.
Yep.
Uh, This is exactly private in the C++ and Java sense. Because of its usefulness, the object system this chapter gives syntactic support. So by adding a variable identifier as the method head, this implicitly creates a name when the class is defined and binds it to the variable. For example, this method head A is bound to a name. The variable A is only visible inside the class definition. An instance of C can call method A in any other instance of C. Method A is invisible to subclass definitions. And the reason that is, because it's not very clear why that's true, given that a subclass will quote unquote inherit this. But if you see how that is translated, you're going to see that this is abusing the lexicoscoping thing. So this is not actually a method per se, because we're actually using a variable to hold it down. And then if it's a variable, such as an attribute, that's not shared. So that's how we get away with that. An instance of C can call method A. Yeah, method A is invisible to subclass definitions. This is kind of horizontal visibility. It corresponds to that. As figure shows, private C++ and Java is very different from private. In Smalltalk and Oz, private is relative to the object in its classes. In Java and C++, private is relative to a class and its instances. By using an escaped variable identifier as a method head, this syntax indicates that we will declare and bind the variable identifier outside of the class. When the class is defined, then the method head is bound to whatever the variable is bound to. This is a very general mechanism that can be used to protect methods. It can also be used for other purposes. Here's that is exactly the same as the previous case. Yeah. This creates a name at class definition time, just like the previous case, and binds the method head to it. In fact, the previous definition is just a shorthand for this. So here you can see why the subclasses won't inherit.
Yep.
Letting the programmer determine the method label allows to define a security policy at a very fine grain. The program can pass. Yeah, so in a way, in a very funny way, this justifies the whole shenanigans about capitalized things in OOP languages. Because I always found that to be like a silly convention, like a silly choice. Oh, if you have capital, you are, I don't know, private. If you have non-capital letter, you are public. But this actually justifies it now. Justifies
Yeah.
in like in a acceptable way.
Yeah, because like in this case, it's the reason it's private when it's capital is because, well, if it's capital, that means it's a logic variable, so it's bound to something. And the default interpretation is it's bound to a fresh name value that's unforgeable and only you have access to it. So that's why it's private.
Yeah, but I'm very certain that if I go to Dart programmers and I ask, okay, is this convention there because they are using this mechanism? They will say no, that is just a convention.
Yeah,
That
that's
is
very
just like a
silly.
syntactical choice.
That's very silly.
Uh, by default method, oh, and just a disclaimer, I'm not a Dart programmer, but as far as I remember, Dart is one of those languages that does that. Or maybe it was Go, I don't remember. Although Go doesn't have OOP, so maybe it's not Go. Protected methods. By default, methods in the object system of this chapter are public. Using names, we can construct the concept of a protected method. In C++, a method is protected if it is accessible only in the class it is defined and its descendant classes. Or its descendants classes. And all the instance objects of this class. Okay, so this is a little bit weird worded because this is up and down then.
Yeah, it's like if you look at the if you
Oh,
look
but
at
it
the
doesn't make sense to be
inheritance,
up, so it's only down, my bad.
yeah, it's down into the side, but not
Yeah.
up.
Yeah, no, so it's across. I was trying to imagine the imagery, and the
I,
protected concept is a combination of vertical and horizontal.
I think it's more like a triangle actually.
Exactly. It's more like this, right? And then this is the
Yeah,
horizontal, and this is yeah. Uh, let us show how. Actually, it's an upside down triangle. Yeah, because you are the beginning. Because it's only the descendants. It's only down. So it's this. Uh, let us show how to express that. So in here we're gonna use, yeah, we're gonna use a trick using the attributes. So the Java notion is protected somewhat different. We left it as an exercise. Okay, anyway, so you have this attribute that holds the A, and then when you were deriving it, yeah, so it is protected because the attribute PA stores a reference to A. Now create a subclass. We can define a method A as follows in the subclass. Bam. Method B access the method with label A through the attribute PA, which exists in the subclass.
Oh yes, because it's inheriting that attribute from the C.
The method label can be stored in the attribute because it's just a value. Yeah, but why is this, like I can see the vertical, but why is this horizontal? Oh, because this is a logic variable, which means everybody horizontally defined will also have access to this, the same.
Yeah, yeah.
Okay. Attributes are always private, so you need to do getters. The only way to make them public is by means of methods. Because of dynamic typing, it is possible to define generic methods that give read and write access. Well, but this is more like, we're gonna see this later. The class inspector shows one way to do this, and the class inheritance for inspector have all these attributes potentially be public. Atom attributes are not secure since they can be guessed. We should use names. Yeah, and then there is the discussion, atom or names. Atoms are visible throughout the whole program, and names are visible only in the lexicoscope of their creation. So atoms is for public things, and names should be for private things.
Very straightforward.
Yeah. Yeah, but then we go to the most popular OOP languages only support atoms. Because, well, they don't have logic variables to begin with. Yeah, this is saying the same thing as before. Oh yeah, actually this matters. When writing a large program, a method can be called from anywhere by just giving its print representation. On the other hand, with names this is more awkward. The program itself has somehow to pass the name to the caller. This adds the complexity to the program as well as being a burden for the programmer. So atoms win out both for program simplicity and for the psychological comfort factor during development. I would argue that the psychological comfort factor could be worked around in local development environment. So you may have a P like a truth, like a table that maps the names to their actual atom representations just for the sake of you when you're programming it, and that's not committed to production. So something like that. It is impossible to have conflicts with inheritance. Second encapsulation can be better managed. Oh, well, names have these advantages, yeah, because you can have conflicts with inheritance, not with names. An object reference doesn't necessarily have the right to call all object methods. Therefore, the program as a whole can be made less error-prone and better structured. A final point is that names can be given syntactic support to simplify the use. Yeah, this is kind of sort of what I was talking about. For example, in the object system of this chapter, it suffices to capitalize the method head. Forwarding and delegation. I never heard of these concepts before.
I have. Delegation is kind of big in C Sharp, I think, as an alternative to inheritance.
Okay, didn't know
But
that.
I don't really use C Sharp, so I don't know to what
Well,
extent.
but
But
both
I know
of
it's a
them
thing.
are like replacements to some degree of inheritance.
Yeah, forwarding is way simpler, by the way.
Yeah, so the whole intuition about those two concepts is that we're gonna try to make inheritance, but not on the level of classes, but on the level of objects. As you can see in this figure here. So inheritance is defined on classes, and there is a common ancestor,
There's a common
common self.
self, as in the self-reference of the
Yeah,
object, right?
yeah. And in delegation is they also has a common self, but it's defined on objects. And forwarding, there's no common self, and we're gonna see why, and it's also defined on objects. So essentially, we are re-implementing inheritance, but on the level of objects.
Yep.
And you may say, why is that useful? Well, Um, I can see forwarding being less useful because what kind of situation you want to keep the identities of the objects, um, but the objects are so loose that you don't want to bind them by their classes. You want to bind them by their instances.
Well, I can think of one example. What if you don't have classes to begin with?
Uh, well, sure. If you have to do it because you cannot run from it, sure. But it's more like you have the option of going the class way while you would do in the object way for specifically for forwarding. Because for delegation, I actually can see a few cases that you want to like you want to make corner cases. You want to jump some. You have a class hierarchy thing, but you have a corner case that needs to jump some of the chains. Then you can use delegation. Uh, but for forwarding is a little bit harder for me to imagine. Like, okay, I want to keep them separate, so I don't want to jump. Uh, they are separate objects, but they need to be rearranged in a different way.
Well, forwarding is useful if you want to implement like some kind of filter, right? Where you have an object, you want to allow a part of a program to send messages to it, but not arbitrary messages. So what you do is you make another object that looks at the message, sees if it's allowed or not,
Mm.
forwards the one that are allowed, and discards the other ones.
Okay, so that is like you have an accessory, like you have a transformation that doesn't make sense to be married to the class hierarchy, but you want to be able to connect to like a pipeline of transformations. So you just put it on the beginning and you forward that.
Yeah.
Okay, that's cool. That's a valid example. Okay, so should inheritance can be tricky to use because it implies a tight binding between the original class and its extensions. Sometimes it's better to use looser approaches. True approaches are forwarding and delegation. So both are defined level of objects. If object 1 does not understand message M, then M is passed transparently to object 2. And forwarding and delegation differ in how they treat self. In forwarding, object 1 and object 2 keep their separate identities. A self-calling object 1 will stay in object 1. A delegation there is just in delegation there's just one identity, namely that of the object 1. A self-calling object 2 will call object 1. We say that delegation, like implementation inheritance, implies a common self. Uh, Forwarding does not imply a common self. Well, because they have separate identities. Now we're going to see how to implement that. So the forwarding has this piece of code, which is way better to read than the delegation one. Yeah, so we are using the otherwise thing, essentially. And if you don't understand what's coming, you try to see if you have like um, somebody to pass the message forward. And if you do, you just call them. And if you don't, you just blow up. So objects created with that that lets them set dynamically the object to which they will forward the message they do not understand. So here we have an example. So you have C1 and C2, and then we're saying we're forwarding a message from 2 to 1. Yeah, 2 to 1. So if you receive a square thing, no, if you receive a cube thing as C2, you will not be able to understand, and then you forward that to object 1. Delegation is a powerful way to structure a system dynamically. It lets you build a hierarchy among objects. Instead of an object inherited from a class, let an object delegate to another object. Delegation can achieve the same effects as inheritance with two main differences. The hierarchy is between objects, not classes, and it can be changed at any time. Yeah, this is also another point that I haven't thought about. So like, you can change. Well, but in OS, does that matter really?
In
Be-
NOS it does, but in Common Lisp it wouldn't, because in Common Lisp you can actually mutate a class to have different ancestors at runtime, which is kind of crazy.
oh, wait. But you're right. In OS, that matters because these are like
Yeah,
procedures.
yeah, because in NOS classes are immutable, right?
Ah, okay.
The
So,
instances are mutable, but the classes themselves are not.
well, not. Well, it depends. They could do the trick that they will explain here, reflection, and probably you can get around with that. Probably, maybe. Because they have an example that you are changing how the new works. So like very common Lisp thing to do, like very meta. And probably you can put a way to allow dynamically to change the hierarchy of the classes, maybe.
I mean, if you override if you make a new meta class, then you can override new, but that doesn't affect the existing classes, only the ones that are based on this meta class.
Oh, you're right. You actually do need some sort of mutation to make that happen then. Given initial objects, object 1
Yeah.
and object 2, you suppose there exists a method set delegate such that this sets object 2 to delegate to object 1. In other words, object 1 behaves as a superclass of object 2. Whenever a method is invoked that does not define object 2, the method call will be retried at object 1. Delegation chain can grow out to any length. If there is an object 3 that delegates to object 2, then object 3 can climb up the chain all the way to object 1. Yeah, and this can happen at runtime. This is actually the part that matters, because just reading this is like, yeah, you can just do this with inheritance. But the thing of the matter is that this can change at any time, and with the classes inheritance, you are kind of stuck after you run the first hierarchy definition.
Yep.
An object property of the delegation semantics is that self is always preserved. It is a self of the original object that initiated the delegation chain. It follows that the object state is also the state of the original object. In that sense, the other objects play the role of classes. In the first instance, it is their methods that are important in delegation, not the values of their attributes. Let us implement delegation, and then there is this code that is very hard to read, in my opinion, because you have to remember a bunch of new moving parts, such as the this, and there is a try with this, and what the heck is
Yeah, no.
SS?
Yeah, no. Compared to forwarding, this is way more complicated.
Yeah, I actually didn't try that much to understand it, to be honest, because like I already got the concept. There's probably a bajillion ways to make it happen. Um, yeah, and then we have the original syntax versus delegation syntax. These syntactic constraints could be eliminated by an appropriate linguistic abstraction. We give an example how the delegation works. We define two objects, 1 and 2, and we object 2 delegate to 1. We give each object an attribute I and a way to increment it. With inheritance, this would look like as follows. So this is using increment 10, and this is using increment 100, and that's essentially all that matters. And increment is only defined in C1. With a delegation implementation, you get the same effect by using the code of figure 710. Yeah, so this is the normal way, like the high inheritance way, and this is the delegation way. And as you can see, it's way more code to read. It is more verbose, but it's only because the system has no syntactic support for delegation. And note that this just creates a surface, scratches the surface what could do with delegation. For example, by calling setDelegate again, we could change the hierarchy of the program at runtime, which is what Marinho said. Doing this call several times shows that each object keeps its own local state. That object 2 inherits the inc and sim methods from object 1, and that object 2 overrides the browse method. Let us make the delegation chain longer. So there's that. Object X inherits all of its behavior from object 2. It is identical to object 2 except that it has a different local state. The delegation hierarchy now has 3 levels, X, 2, and 1. Let us change the hierarchy by letting X delegate to 1. And then in the new hierarchy, object X inherits its behavior from object 1. It uses the browse of 1, and it will increment by 10 instead of 100 because 1 increments by 10, not by 100 in the browse.
Yep.
Yeah, not very straightforward. Again, they're probably like, man, a program that requires you to change the hierarchy at runtime. I don't know if I don't have immediately an example on that fits.
Well, any language with an interactive session like Common Lisp, Smalltalk, kinda needs this, no?
In which sense they need it?
Because if you're doing interactive development, you want like if you redefine a class, you want the existing instances to use the new definition, no?
Well, yeah, but that's not that's an implementation, like that's required because of the interactiveness. That's not required because, oh, actually there's this problem in the real world that actually benefits from using runtime defined hierarchies. Like I'm kind of trying to think of a problem that I would use this to solve it, not
Well, isn't
as an environment. As an environment, sure, you need it for interactive development in Common Lisp and stuff.
well, it solves the problem of having a decent user interface for an interactive environment.
In RPG, the skill tree is mutable.
Huh, that's actually kind of interesting as a concept. And yeah, it would benefit from this, I think.
Yeah. Okay. A system is reflective if you can inspect parts of its execution state while it is running. And well, we already can stop there. Running which portion of it? Because if you're running your compilation process, then it's compile time reflection. If you're running the program, then it's
That's runtime
runtime
reflection, which
reflection.
is a whole nother beast.
Yeah. Reflection can be
Well, give,
pure. Go on.
well, given that this is Oz, you can assume it's runtime reflection. But yeah, in general, you may want to make that distinction.
Yeah. Reflection can be purely introspective, only reading, or intrusive, writing. Reflection can be done at a high or low level of abstraction. One example of reflection at a high level would be the ability to see the entries of the semantic stack as closures. It can be explained simply in terms of abstract machine. On the other hand, the ability to read memory as arrays of integers is a reflection at low level. You cannot do that in an abstract sense. Okay, OOP in programming is particularly fertile for reflection. For example, the system could make it possible to examine or even change the inheritance hierarchy while a program is running. We've just seen this before, but with objects, not with classes. The system could make it possible to change how objects execute at a basic level, how inheritance works, and how methods are called. So you're essentially like it's almost like having a type system, but while the program is running, you change the type system.
Yeah, the trick they do to enable this is to define a class as just a particular kind of object, which has a class of its own, which is called a meta class, and you can mess around with the meta classes to make them do new things.
Yeah, this is a very dynamic, usually like very dynamic behavior. Like you can change things that you usually would think are built-in immutable things about the language, but you
No,
can
they're
change them.
customizable as well.
Yeah, and you can change them. So I don't know. You can start with a simple system F omega type system, and while the program is running, there is an if that changes to dependent types. Like
There you go.
I don't know why would you do that, but you can. And this is kind of the okay. And actually, this is a little bit of a side at a tangent. I think this is a little bit of a fetish of dynamic people. They understand that it's powerful in a destructive sense, but they want the ability to do it. They love the fact that they can wake up and say, "Man, I can just change this at runtime." They know it, like, and if you ask them, do you understand that this is a very powerful thing and this is completely against the whole rationale of programming with less constraint-based programming? You know that. And he said, "No, we know, but we want the power, we want to think that we could destroy everything." That's essentially how I interpret that.
Yeah,
Um, a description of how an object system works at a basic level is called a meta-object protocol. The ability to change the meta-object protocol is a powerful way to modify an object system. Meta-object protocols are used for many purposes: debugging, customizing, and separation of concerns. Meta-object protocols were originally invented in the context of clause, of course, especially because Common Lisp has very interesting and impressive, because of its dynamic nature, it can give you like weird diagnostics. I don't know if you can read like the registers of a computer, but the the interactive development is very powerful. You can inspect a bunch of stuff. A common use of meta-object protocols is to do method wrapping. To intercept each method call, possibly performing using defined operation before and after the call, and possibly changing the arguments to the call itself. In our object system, we can implement this in a simple way by taking advantage of the fact that objects are one-argument procedures. For example, let us write a tracer to track the behavior on an object-oriented program. The tracer should display the method label whenever we enter the method and exit a method. So we make a new, but as Marinho said, you're not changing the other people that are still using the old one. You're just creating a new one available to be used that is essentially doing the same trick but doing browse before and after. Um, it behaves identically to the old one aside from the prints. It uses high order programming because this is a function. Well, this is a procedure. In a second way, it's with a class instead of a procedure, which is kind of funny because this is what this sugars to, but you want to use this sugared version for some reason.
There's a slight semantic difference, and the text talks about it. Because if you just use the procedure directly, the one above,
Mm-hmm.
that's simpler. It's easier to implement and reason about, but it's less powerful because you can only intercept the calls coming from the outside, right? If you define a method to call another method of the same object, you won't be able to trace that.
Repeat that. If you call a method,
If you call a method of the object, and inside of that method it calls another method on the same object, the trace is not going to print that second call, you see?
sure. This only prints for classes in class instantiation, right?
Yeah,
This doesn't do anything about the methods.
yeah, the second one, because you're defining it as a class and then you are inheriting from it, then you actually can trace the
You
calls
can
that
put the
go
hook
to
on it.
self. Yeah, you can put a hook on it by using the otherwise.
Yeah. This uses dynamic class creation, the otherized method, and a fresh name tnit for the initialization method to avoid conflicts with other method labels. Very clever. And reflection on object state. Yeah, this is also very powerful stuff. So essentially, you want to have a void star. So how you do that? Using reflection. So you can have an object of any class, and you want to be able to store the state of that in a variable. So creates a clone of self and binds it to X, whatever self is. The clone is a new object with the same class and the same values of attributes. ToChunk binds X to a protected value that contains the current values of attributes. And FromChunk does the opposite. It sets the object state to X, where X is obtained from the previous call. So there we have it. We have a counter. We initialize the stuff. And then we can literally create like pass states around just by using ToChunk and FromChunk. Very
Yeah.
powerful stuff. It's generic, so it doesn't matter which class it is. But I would like to know what the fuck happens if C2 was from a different class. Like, how would that work?
I'm guessing. I'm guessing it would.
Do they have a check for that in the beginning of from, or do they just let it fail?
They would probably check if the class matches and fails if it doesn't. I'm guessing, because that's what would make the most sense, I think.
I don't know if they would check it. That's actually maybe I'm not putting fair faith on them, but
I mean, this is DOS, it's not like it's JavaScript.
what a what a statement. Okay, I have 10 minutes. Let's speed this up. So 7.4. Programming with inheritance. The correct use. Yeah, I want to know what the fuck is the structure view. Because the way that it's saying, it's essentially saying that this is a structure view. Well, this. But it's not really clear, and I feel that the authors like this is so bad, we're not gonna tell what it is. Man, this is for educational purposes. Come on. So uses of inheritance. You have two uses, what they call the type view and the structure view. So the type view is actually uh, something that reminds referential transparency. Right? That's one way to put it. Because they are calling substitution property. The type view is consistent with the principle that classes should model real-world entities or some abstract versions of them. They satisfy the substitution property. Every operation that works on an object of C also works on objects of a subclass of C. So yeah, so you can replace one with the other, and the invariants are preserved. So that reminded me a little bit of referential transparency. It's not the same thing, just to be precise. It's not the same thing. Pedantic Marinho can relax. I'm just saying that it reminded me of like, okay, you swap it, properties are preserved. Nice.
I
Um,
mean, the thing about the structure view is that okay, you can take the type view and say okay, a subclass is strictly a subtype, and you should
exactly,
program it as such. But
exactly.
you don't have to do it, and if you don't do it, you are taking the structure view, right?
Yeah,
That's the
yeah, but that's very bad because you are breaking variants, and we're gonna see.
Oh yes, I remember actually reading a paper a while back about oh, you can implement like a sets as a subtype of multisets, and
Yeah,
that works if you use inheritance, but it doesn't respect the type view because you have methods that do one thing on a multiset, but they do different things on a normal
yeah,
set, right? Like
yeah,
adding a value to the set.
yeah. Um, a structure view. Inheritance is just another programming tool that is used to structure programs. Okay, so that's very bad because it's not the detailing anything. But what it means is that you are just using it for convenience, like to try to extract commonalities probably. But there isn't any properties that are preserved between the hierarchy of the classes. So you're not treating them as subtypes. You are treating them as just convenience. This is strongly discouraged because classes only satisfy the substitution property. The structure view is an almost unending source of bugs and bad designs. Major commercial projects, which we're not gonna say, like this is funny, have failed for this reason. And then there is AFL, which, well, Mageta was the first one that introduced this language to me years ago. We never programmed in it, but I know it exists. Are designed from the start to allow both the type and structure views. Yeah, but you don't need to allow a language to have structure view. This is a semantic difference. This is not an implementation difference. Uh,
Yes, you are correct.
well, maybe there is an OOP language that actually checks the substitution property. Maybe. I'm unaware.
How will you go about checking that though?
You you have to prove it, much like
Well,
proving type classes. Like Haskell doesn't force you to do that, but there are languages that apparently do. So you could just
well,
say, hey, this subclass is from this class, and you haven't proved to me that this substitution property holds for this
that
method.
sounds that sounds like it would require dependent types.
Probably, maybe, but uh, that's one way. That's one way to like, okay, there is an implementation difference. This is not just a semantical difference.
It also sounds like it can very easily run into the halting problem.
Yes, yes, I agree. In the type view, each class stands on its own feet. This is even true for classes that have subclasses. From the point of view of the subclass, the class is identity with sole access to the methods and its attributes hidden. In the structure view, classes are sometimes just scaffolding, which exists only for the sole. Yeah, so that's what I mean by convenience. You have commonalities, you don't do copy paste, so you use that for that. In the vast majority of cases, inheritance should respect the type view. Yes. Man, I think
Uh,
I found an example of where the structure view kind of makes sense. You are modeling something that is not real. You're modeling just like tooling. So you have like, instead of having utils, you have um, you're just defining the utilities functions as classes, and you can try to structure them in a way that they have commonalities. For example, collections, right? You have lists, you have sets, you have multi-sets, and you may want to add to them, to all of them at the same time, something, such as, I don't know, their name. So there is a method that gives you the name, and you make an abstract superclass just for the sake of organization. Like the gain is not huge, but at least uh, you this can be used. Because in the majority of cases, we try to mesh a real-world understanding of entities through the class hierarchy, because a lot of things can be understood as that. Uh, I don't know. The structure view, like we don't have examples here, so. Doing otherwise gives you subtle and pernicious bugs that can poison a whole system. Let's give an example. We can take as base class the account class. The first extension is conservative, so you have the verbose account. There we go. We simply add a new method, verbose, since the existing methods are not changed. This implies that a verbose account object will work correctly in all cases where an account object works. Let us now do a second, more dangerous extension. Yeah, I think this is not great because you could theoretically also have the fee in the original account and the fee is zero there.
But the point is that for that to work, account with fee would have to be the superclass, not the other way around, you see?
No. Well, yes, I would make the account with fee the superclass because it's trying to make like a property. This is the where is the property? Here. It's saying this is the invariant. And this extension breaks that invariant. So it's bad. But this is still solvable because you can just say that phi is 0 on the super. And this is the invariant now. This.
Yeah, and to make this work as a proper type hierarchy, you would have to flip the order, as I mentioned.
Yeah. The problem is that account phi does not work correctly when viewed as an account object. They do not satisfy the same invariant. Typically, the origin of the break will not be obvious since it is carefully hidden inside a method somewhere in a large application. It will appear long after the change was made as a slight imbalance in the books. Debugging such as slight problems is amazingly difficult and time-consuming. Well, yes, very yes. Partially because these invariants are only being held in the brain. Nobody is actually well. You should, if you are doing this, you should have tests for it, and they should break when you introduce this. So that's one way to go about it. And this is also kind of the same thing that I think we already mentioned this before, that dynamic languages rely more on tests than static ones. So you would have tests on both in this case, but usually dynamic languages have more because of the everything's done at runtime. Typically, I already read this. The rest of the section considers the type view. Yeah, we should use the type view. That's okay. A well-known company initiated an ambitious project based on object-oriented on OOP. Despite a budget of several billions, it failed. Among the reasons for failure, there were two major mistakes. Substitution property was regularly violated, so corner cases. This made it much more difficult to use objects. Instead of one routine being sufficient for many classes, many routines were needed. So you have to override a bunch of times. Classes were subclassed to fix small problems. So this is for patching. Yeah, this is such
Wait,
a nasty use case.
that's kind of silly, right? Like, you own the code base, you have access to the original class. Why don't you change that instead of making us? Yeah, that doesn't make any sense, I don't think.
It does, but okay, let me explain why it does. Your system is so heavily uh, imagine a very mutable system. Imagine a system that uses global variables and it mutates all over the place. This makes sense if you noticed that, hey, this is doing a -1 and this is wrong, but the balances is right. That means that somewhere other in the chain somebody's doing a +1, but you don't know where it is. So what are your choices? You can fix it and let it break and try to discover where the plus one lives to also remove that. Or you can do the lazy way and don't touch it. Let it like be fragile and finicky and very and like unstable. But you do a subclass that for your cases from now on will assume that the minus one is not there.
In other words, build a house of cards
Exactly.
and hope nobody blows on it.
Exactly. So this is why this is here, because at first glance you have the code. Why the fuck you would not fix it? Why would you subclass with a patch? And the only
Because you
use
have so much
case.
spaghetti that you would have to travel through the spaghetti
Exactly.
lanes to find the
Exactly.
problem.
Well, to find the other lack of balance on the other side, because if the books is right, if the outcome is right, and there's a minus one wrong, somebody is counterbalancing the minus one. So
But doesn't that imply that somebody else already did this subclassing to fix a small problem elsewhere?
not necessarily. Maybe the understanding back then was wrong. Like, maybe they thought the minus one would be correct and the plus one there would be correct, and that was fine. And then later they discovered actually this is wrong, and we should not have this minus one in the first place. But then, okay, where is the plus one that counters that?
Uh,
Nobody knows. Everybody that knew left the company.
which was
Uh,
very wise, I think.
uh, but that's exact. You said perfectly. You have too much spaghetti and you have to run through it. So instead of doing that, you just let the knot of spaghetti lives, and you just extend
And
it
you
with a
add,
patch.
yeah, you add more spaghetti to fix the spaghetti.
Obvious invocations are down by an order of magnitude. The class hierarchy became unnecessarily deep. The lesson to heed is to be careful with inheritance. Respect the substitution property whenever possible. Use inheritance to add new functionality. Study common design patterns. Yeah, re-engineering. This is just refactoring. Like, what the fuck is this? What the fuck is this warming the brain?
You have to remember, Lemos, this is a relatively old book.
But refactoring. Like, are you telling me that this term is older than refactoring? Come on.
It might be.
Come on. Come on. We should mention the discipline of re-engineering, which is can be used to fix architectural problems like the above. The general goal is to take an existing system and attempt to improve it of some of its properties by changing the source code. Damn, you would not change the source code. Many properties can be improved in this way. Blah 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 blah. However, an engineer cannot resurrect a failed project. It's more like curing a disease. If the designer has a choice, the best approach remains to prevent the disease, to design a system so that it can be adapted to changing requirements. We've seen this before. Constructing a hierarchy by following the type. So then we go back to all the way to section 342, and we remember a tip that we got that usually functions dealing with a type mimic the type structure. Then we go back to the list and say, okay, we are OOP folks. How can we use the same principle in here? Well, you need to use the type view, and you use the type view, you're gonna make a list class that is abstract, and you're gonna make subclasses for the two cases of new and cons. And I never thought of doing that this way, to be honest.
I mean, it makes sense, right?
It makes sense, but I never like thought, okay, how am I gonna implement a list in OOP? Never thought of that. Um, yeah, so abstract class, which means the methods are not defined. It's the responsibility of the concrete classes to define it. Um, so nothing too crazy. And yeah, it looks terrible, right? This, like, what the heck is going
Well,
on?
because well, you don't have dedicated syntax for lists in this case, right?
Yeah,
So you're kind of screwed.
yeah, and then we go all the way to generic classes. So this is essentially getting close to a type class now, because you want to be able to sort something. So here it is. You want to be able to provide a quick sort for many different types. But you have a requirement. They have to implement less than equals or whatever. So you can do this way. So you can inherit from generic sort, provide a less, and you have quick sort. This is pretty similar to a type class. And Haskell is from the 90s. They should mention that.
I
Um,
think, yeah, and then it shows the alternative approach using higher order procedures, which I think is nicer, probably.
um,
Yeah, 7.17, the
the
figure.
only thing that matters is the runtime thing, right? Because with the class you cannot change this at runtime, but with the function you can.
Ye- yes, I guess technically the downside of the nicer approach, which is using the procedure, is that the language has to support that, and not every language supports that,
Well, but
right?
that's a kind of kind of like meh argument because this is us. This is already like 95% that nobody does. So like, sure, but you can say that for everything. So
I find it funny that you can take the higher order approach in Zig, but not the inheritance one, which is usually the other way around, right? Like if you look at Java, for example.
wait, you said that you can do the nicer approach in Zig.
Yeah, because you can make a
Yes.
function that returns a type in Zig.
Uh-huh. Remember that. A generic class is one that defines the functionality. It has to be completed before it can be used. Let's do two ways to define generic classes. The first way is using inheritance. The second way, higher order programming. Uh, yeah. The first way is just a syntactic variation of the second. Makes complete sense. So using inheritance is what I just said, right? You have a generic sort class and you inherit from it providing the requirements. Very
Yep.
similar to a type class. And the second way, you have a function that instantiates a class, well, creates a class, it's creation time, using the last operation that you provided. So
Yep.
yeah, it's used here. Cool. And this is how you do that using the higher order approach. I don't think this is okay. Okay, it is clear that we're using inheritance to plug in one operation to another. This is just higher order program, a form of higher order programming, where the first operation is passed to the second. What is the difference? In most programming languages, the inheritance hierarchy must be defined at compile time. This gives a static genericity, but well, in OS it is at runtime, but you cannot change it. So there's also that. But it is static. The compiler may be able to generate better code, blah blah blah. However, programming, when it's possible, to find new classes at runtime. This gives a dynamic genericity, which is more flexible. Now, multiple inheritance, and this example is very cool. Very cool. But we already are over now, so let's speed this up. So the problem that we want to do is to be able to make a graphic library, a graphics package that allows us to compose figures. Compose figures. So
Yep.
what are we gonna? We have a generic class called a figure. We have a line that inherits from figure. We have a circle that inherits from figure as well. And then we make a group called linked list class that will essentially iterate through all of the elements of it and do the thing.
Yeah, for all. Very
Yeah, for
nice.
all. It's specifically interesting because it uses first class messages. A linked list is represented as a sequence of instances of this class. A linked list is represented as a sequence of instances of this class. The next field of each instance refers to the next one in the list. Wait a moment. Okay. The last element has next equal to null. The header is also null in the beginning, so this is never an empty list. And then here's the kicker. We can make composite figure that inherits from both, which is the cool thing because you can inherit from the figure and you can inherit from the linked list. What that gives you, well, first of all, this use is correct because they are completely orthogonal. They don't have interactions and conflicts with each other. The init method is careful to initialize the linked list. It does not need to initialize the figure. As in all figures, there is a move and a display method. And why this matters? Because we want to interpret the composite figure as a single figure. But the thing that is interesting is that the composite figure is It's a combination of multiple figures together. So we can say that a composite figure is a figure by doing the multiple inheritance in this case.
Yep.
Um, yeah, so you can see here, this is the thing. This is actually the thing. You're doing for all of the inner figures of the linked list, and you're using self because for all doesn't exist in here, so it must come from here. You're calling move, which comes from here. Well, this is the move for each one of them. This
Yeah.
is the move for each figure itself. So very, very cool. Very cool.
I think this
Uh,
is a really nice example.
this is very cool. Yeah. It does not need to initialize a figure. Blah blah blah. Do you see the beauty of this design? With this, a figure can consist of other figures, some of which consist of other figures, and so forth. So you can compose the composite as well in this way, because this means that a composite is a figure. So you still have move, but they're kind of like on the first level, you kind of can interpret the circle and the line and triangles. They move by themselves, but you have the impression that they move together. And when you compose the composite, the entire square moves. So it's really cool, really cool. And we have an example. So here we create a window, we create a triangle, we create a circle, and then we display. And F1 is a composite. And I don't know how this works, but apparently they can make it move. They have animations. They have an animation engine, which is cool. And then there comes a second approach, which is use association instead of using inheritance. What the fuck is association? Is when you are
It's basically
nesting the
composition. Yeah.
functionality not by using multiple inheritance, but by using attributes.
Yeah, basically composition.
So you have the list thing, the linked list internally, and you just inherit it as a figure. There is a yeah here with multiple inheritance, a composite figure is also a linked list. So you have more, you have better syntactic support for using the methods of the linked list. Or the operations of linked lists can be used directly on composite figures. This is important if you want to do linked list calculations with composite figures. With single inheritance, a composite figure hides its structure. This is important if you want to protect the composite figure from any calculations other than those defined in its class. So this means that there are a couple of methods that the linked list will provide you that you don't want the composite figure to have.
Yeah, this is a classic
Too much
encapsulation
power.
versus flexibility trade-off, right?
Yeah, exactly. Well, not only that, but it may also be too dangerous. Like allowing you to use linked list methods on a composite figure may, I don't know, give you some risk because the linked list class provide you some very powerful methods. Well, in this example, it's kind of silly because everything is graphics, so nobody's gonna launch a bunch of missiles doing that. But uh, maybe you have other situations where exposing these methods via inheritance is gonna be dangerous and leak some data, such as the encapsulation case. Yeah, so conclusion. Many of the figures can be defined from inherit from figure. Figures are tied to the canvas. This has the advantage. Yeah, this is like future things. Very future things. So a journaling facility can be added. That is, it should be possible to record the sequences of drawing commands. Yeah, again, this is just if you want to continue the graphics package. The display method should be able to pass arbitrary parameters from the application program through the graphics package. The adjoint operation combines two record arguments, where the second argument overrides the first in the case of conflicts. This allows arbitrary parameters to be passed to display to the canvas drawing command. And then finally, rules of thumb. Oh man, there's still UML. Oh, there's many things still. We're so fucked. Okay. I keep forgetting. I read this yesterday and I already forgot. Multiple inheritance works well when combining two completely orthogonal abstractions. Multiple inheritance is much harder to use correctly when abstractions have something in common. So there's an example. Yeah, implementation sharing problems. What happens when sibling superclass share a common ancestor class that specifies a stateful object? Yeah, this is the root of the problem. This is known as implementation sharing problem. This can lead to duplicated operations, happens when initializing an object. The initialization method usually has to initialize its superclasses, so the common ancestor is initialized twice. So this is essentially like you have, what is that? You have an you have
Yeah, this is the classic diamond
hexagonal.
problem,
Yeah,
right?
hexagonal. So you have diamonds. No, it is the diamond. Sorry, not hexagonal. It's four sides. So you have two in the middle. They inherit after a bunch of indirections the same, and after a bunch of indirections downwards, they also are the superclass of one. So you have like the shape. Yeah, this is, and especially if you have a stateful object, this is gonna be a pain. When name clashes occur, the same method labels used for adjacent superclasses. Thus, the method must define a local method that overrides the conflicting causing methods. I didn't even know you could do that. Right, this is the first time it is explicitly said that conflicts can be solved. I thought they would just be impossible.
Yeah. Also, actually, most languages that support multiple inheritance, they actually define a linearization rule that says, okay, if the same class appears in multiple times in the ancestor hierarchy, actually it only appears once, and there's something called the C3 algorithm that a lot of languages that do multiple inheritance implement. But yeah, in general, if you don't know about that, you do have to solve this problem somehow.
Okay. Purpose of class diagrams. Yeah, so this is just justifying why UML exists, which is kind of funny. Because it doesn't depict a bunch of stuff, such as does not specify the functionality, model the dynamic behavior of the application, like how it evolves through time, especially in a dynamic language like OS or Common Lisp. They only model one level of its application component hierarchy. So like, yeah, you need a bunch of diagrams to make this worthwhile. So he's talking about this diagram.
Yeah.
Oh, and I should say that this is cardinality. I should make like honorable mention to cardinality.
Yep.
Yeah. Okay. Design patterns. So what is this? This is essentially abstractions that through time some people classified as worthwhile to write about them, so more people can use those abstractions to solve their problems. So they call that a design pattern. So it's like if you have this type of problem, this is a particular solution that worked
Yeah.
for me.
Yeah. Shorthand is go read about the previous book that we did on book club if you want to know more about it.
Good segue. I haven't thought of that. In declarative programming, yeah. So we already seen this before.
Yeah,
Design
we saw this
patterns.
in yeah we saw this in patterns of software.
Yeah, as well. No, but in this book as well. So you have a pattern here, design pattern, which is using like making functions that deal with the type, usually follow the type structure, and security with capabilities, rapid functionality in a secure layer. And now we're going to talk about the composite pattern. Yeah. So the composite pattern is this diagram. So if you can swap the names for your particular case, an argument is being made that you can use the composite pattern, design pattern. The purpose of composites is to build hierarchies. Give a class that defines a leaf, the pattern shows how to use inheritance to define trees. So you have the diagram. The usual way is to use this pattern is to plug an initial leaf class, so leaf. Then the pattern defines both the composite and component classes. So usually a design pattern also gives you stuff for free, in a sense, in the same sense that the type class does. But the type class uses as the base case not OP but functions.
Yeah,
So
this
if
is
you give me
basically
this
a
function, I give you those functions.
yeah this is basically a rose tree, right?
Rows. Never heard of that.
Yeah, rose tree is a generalization of a binary tree where each branch can have an arbitrary number of children, basically.
But that's a
So
B
it's
tree.
no, 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 no. A B tree is not arbitrary. There's a limit. Like it has to be between n and m times 2 for some n, right? A rose tree, the branch is actually a linked list. It can have arbitrary length, whatever you want.
Okay. I thought the B tree with limits were just for application uses. I didn't know it was a definition. of the data structure.
It is.
Uh,
It actually is.
we can use the composite pattern. Yeah, so the component will be an abstract class. We can use composite pattern to define compound graphics figures. The composite pattern is a more abstract solution that is not assuming that the grouping is done by a linked list. Yeah, so the grouping is also generic. You can choose. The composite class has add and remove operations, but does not say how they are being implemented. They could be implemented as a linked list, but they also could be used as a dictionary. Um, uh, what is the name of the cool lists?
Finger trees.
No, 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 not that, no, not that one. The one that we saw here. Difference lists.
Different
Uh,
lists. Yeah, those are also pretty nice.
Given a class that defines a leaf of the tree, the composite pattern returns a class that defines the tree. And put it this way, this sounds like our programming. We would like to define a function that accepts a class and returns another class. Most programming languages such as C++ and Java do not allow define this function. There are two reasons for this. First, they do not have classes as far as class values. Second, the function defines a new superclass in the input class. Most languages allow defining new subclasses, but not superclasses. Yet, despite these limitations, we would still like to use the composite pattern. The urgent solution to this dilemma is to consider design patterns as primarily a way to organize one's thoughts without necessarily being supported by the programming language. A pattern might exist only in the mind of the programmer. Yeah, this is very controversial because this is essentially saying that programming is more than writing a piece of code. And there's a
Oh,
lot of people that disagree with that.
that is very sad.
Jonathan himself, I think he actually believes that programming is just making instructions to the computer. Design patterns can then be used in languages like C++ or Java if they cannot be implemented as abstractions in those languages. This can be made easier by using a source code preprocessor. Yeah, this is a very bad idea.
That's how C++
Very,
was born.
but this is very bad, man. Well, I guess I should say if you do a very silly preprocessor, it's very bad. But at that point, if you're making a smart preprocessor, just make a new language. What are you doing?
Well,
The
isn't a compiler a kind of preprocessor?
Yes, but the preprocessor has the negative connotation of being silly.
That's fair.
The programmer can then program directly with design patterns, and the preprocessor generates the source code for the target language. I mean, if you're calling like this is very vague, so I'm just assuming it means preprocessor in the C sense. But if you're talking about a very smart preprocessor, that's just a compiler. So, okay, that's okay. But I don't know. I don't know if this is worth the effort. Just make a new language, man. Like preprocessor, they should be very simple. If they're not simple, you're doing something wrong.
Well, technically, a preprocessor could also be a macro, right? If you're using a Lisp or something like that.
Uh, yes, but macros are controversial on their own.
Well, yes, but they run before the source code is executed, right? They expand the code, which then gets evaluated.
Yes,
So they are a preprocessor by definition.
yes. So now let's see an example of that using the children. Yeah, using the
Yeah, this
linked
is
list.
yeah. There's nothing surprising here.
Instance of leaf, which provide at runtime the internal nodes for all method invocations to the leaves in their subtree. The simplest way to do this is define a class composite. This class contains a list of its children. You assume that all instances have the initialization in method init. And that's how this also looks terrible, but well.
Well, no syntactic support. So what did you expect?
Enforce invalid trees. This implementation works for any leaf class because of dynamic typing. The disadvantage of this solution is that systems do not enforce all leaves to be instances of the same class. So this is like classic dynamic language problem. Like you have a list of whatever. How do you enforce the whatever? You have to do it yourself because
Yeah,
people
this
don't
is
like.
at this point. Yeah, at this point you're basically re-implementing Racket's contract system in an ad hoc manner.
Yeah. When an instance, well, you're even re-implementing type checking. When an instance of composite is initialized, it is given a function valid, which is bound to the stateless attribute valid. The function valid is used to check the validity of each inserted node. But to be completely fair, if you're using Clojure, you can use schemas or specs or whatever. to try
Yeah.
to avoid, well, to try to automate some of this stuff. Okay. Okay, so next time we're going to be talking about finishing chapter 7. So 7, 5, 6, 7, 8. I think it's, yeah, 7, 8. Uh, Anything
Yeah, this
else?
I just want to say this part of the book that we're gonna do next is really interesting because it talks about, okay, how would you go about implementing this, right? Because until now we just assumed, okay, let's say the class syntax is a given, and we're gonna worry about how to implement this later. Well, we
Really?
just
I thought
reached
we
the
already
later.
seen how to implement it before.
We saw a sketch, but now we're going to dive into the details a little bit.
Cool. Yeah, this was very interesting. I didn't know about forwarding. I didn't know about delegation. I didn't know about well, I didn't know the term association. The example of the composite figures was very cool, very cool.
I
Uh,
think I think all people should read this book. Actually, they may learn a thing or two.
oh yeah, but there is a problem. Like this book has a problem that it doesn't work. Well, it does work well if you read the chapters by themselves, but there's clearly a continuation being done because it keeps doing comparisons. So
Yeah,
if you haven't read the previous 6 chapters, you're gonna have a hard time understanding. Okay, what is this guy talking about in this comparison?
that's fair. That's fair.
But for example, what we just read didn't abuse of that. If you know what is high order programming intuitively, you can read it. What we just read today. It's completely fine. We also saw meta object protocol. We saw dynamic binding, static binding, all very cool stuff. Educational. Reflection, dynamic reflection in this case, runtime reflection. Yeah, this is delegation. What else? Oh, we also saw the atoms versus names in the method heads.
Oh, right, and the different definitions of private methods, which apparently every
Private,
language, yeah,
exactly.
languages have different ideas and they use the same name. That's kind of
Encapsulation.
sad.
But that's human race for you. We love adding ambiguity into our natural languages, man. It sounds like a fetish, but well, I'm gonna finish the recording now.